Hello professor, my name is Gautam and I'll be explaining the second problem of the homework 10. Now we have to define the properties of stochastic process. The first one is the Whiteson stationary process. You can say that a real stochastic process x of t is called Whiteson stationary if e of x of t is constant and rxx of tau is equal to e of xt1 into xt2 where tau is equal to t1 minus t2. Now some of the examples of Whiteson stationary process are Poisson increment, Poisson impulse and random telegraph signal. Now here we can say that x of t and y of t are jointly Whiteson stationary if each one, that is x of t and y of t, is Whiteson stationary and x of t plus tau into y of t is equal to rxy of tau. If a given process is Whiteson stationary, then it does not imply that it is a sextant stationary, as a Whiteson stationary process usually involves first order and second order movements. For independent increments, a given process is called independent increment process if probability of x of ta as x of tb is less than equal to x1 or and x of tc minus x of td less than equal to x2 is equal to probability of x of ta minus x of tb less than equal to x1 and multiplied by probability of x of tc minus x of td less than equal to x2, where ta, tb, tc, td are all non-overlapping intervals and ta is greater than tb, greater than tc, greater than td. Now from here it can be understood that if a given process is an independent increment process, then it also implies that it is an uncorrelated increment. Now for the following examples, Poisson process and Wiener process are examples of independent increment process. For a Markov process, we can say that a process x of t is Markov process if the past has no influence on the statistics of future under the condition that the present is unknown. Now here we can say that probability of x of t1 less than equal to x1, x of t2 equal to x2, x of t3 equal to x3 less than to xn is equal to x of t1 less than equal to x1 and x of t2 equal to x2. Now here we can say that a Markov process can be statistically determined if we know the second order distribution function, that is f of x1, x2, t1, t2 is known. Now some of the examples of Markov process are random walk, Wiener process and random telegraph signal. Now normal process x of t is said to be normal if the random variable x of t1 up to xn are jointly normal for any n and for any value of t1 and t2. Now the density function is given by 1 upon root 2 pi n determinant of c e raised to minus 1 by 2 x minus the mean transpose and c inverse of x minus mean. A strict and stationary process. Now x of t is called strict and stationary if its statistics is not affected by a shift on the time axis. That is, fx of x1 x2 up to xn and t1 t2 up to tn should be equal to fx of x1 x2 up to xn and time is shifted, that is t1 plus t1 plus c and t2 plus c up to tnth of c. Now the above equation should hold good for all values of x and for all shifts in values of time, then the process is called a strict and stationary process. Now from here we can infer that any sequence which is independent and identically distributed random variables, it is a strict and stationary process. Now coming to white noise, V of t is white noise if the autocorrelation function is q of t1 into delta of t1 minus t2. Now where V of t is always assumed to be having zero mean. Now if z of t is a Poisson impulse process, then V of t is equal to z of t minus lambda is a white noise with q equal to lambda, which is constant. Now if x of t is a Whiteson stationary white noise, then q of t equal to q and e of y of t of square is equal to q minus infinity to infinity magnitude of h of alpha square d alpha. Now this can be called as the energy of h of t, where q is the average intensity of white noise input. Now for a mean ergodic process, x of t is called mean ergodic if all its statistics can be determined from a single sample. That is, x of t is mean ergodic if limit t tends to infinity 1 over 2t in the integral with the limits minus t to t x of t dt is equal to the expected value of x of t. Now here we can also say that a Whiteson stationary process x of t is mean ergodic if this we have written it in terms of the covariance 1 upon 2t limit t tends to infinity minus 2t to t c of tau 1 minus tau 2t d tau is equal to 0. Now we can also say that the sufficient conditions for mean ergodicity are, that is, if x of t is WSS and the autocovariance is less than infinity, then x of t is mean ergodic. And if x of t is WSS and limit t tends to infinity, c of t equal to 0, then x of t is also mean ergodic.